Hi guys, how's it going? So we have a question over here that's on the easy side when it comes to difficulty, but it's also tedious. There are just too many forces over here, so it might get overwhelming. So it's not difficult, it's on the tedious side. People often confuse the two, right? So with this question, what I'm going to do is we're going to revise all of what we've studied so far and see whatever we've studied, how is it actually implemented? So I'm going to simplify it as much as possible. We're going to spend some time on this question. We're going to simplify it, and also we'll also try to reflect on what key concepts from the entire chapter, because the chapter seems overwhelming and a bit confusing and very math intensive. So what are key elements that are being implemented here? So in other words, we'll try to solve this question as an O-level student who just got to know a little bit more of math. That's the idea. And using that, let's begin. So let's begin with reading the question. A 2 kilogram cookie tin is accelerated at 3 meters per second square in the direction shown. So this is a cookie tin, it's a top view, it's moving that way, right? With the vector A over a frictional horizontal surface, so there's no friction. The acceleration is caused by 3 horizontal forces. I only see 2, right? 3 horizontal forces, only 2 of which are shown. Okay, should have read the question properly. Force F1 of magnitude 10 newtons and F2 of magnitude 20 newtons. So 10 newtons, 20 newtons. What is the third force, magnitude, and angle notation? So we got to figure out what is the third angle, where is the third force being put in. I'm going to guess it's somewhere like this. That's my best guess, just how forces seem like to me. And this is going to be a little stronger because it's at the end the object is moving towards more right and up, so we have a huge up force and nothing really actually moving the box right. So I'm gonna say it's gonna be something like that. The angle is not going to be too high, it's going to be towards the right hand side. How do we tackle this question? Let's figure that out. Let's bring our attention to the side for a minute and review what concepts are being discussed. All right, the first concept I have is that all forces, if they're equal to each other, well, they'll be equal to each other. So you can have 2 forces or you can have multiple forces. If they're equal to each other, their components are also equal to each other. And I hope that makes sense. We've already kind of gone over this and we should know this, but just to reiterate, if force A is equal to force B, that object is stationary. So it's resolved forces in the horizontal direction. These two are in the horizontal, these two are in the vertical direction. In the horizontal direction, they are equal because for the forces to be balanced, the object is not moving. So if we look at any particular component, looking at the horizontal component, the object is not moving towards the left or moving towards the right. So that means all of the horizontal forces are equal to 0. Makes sense. Same with the vertical. All the vertical forces are equal to 0. Now, a lot of times what you see is if a force is resolved, you'll see in the horizontal direction, you'll see FAX, or they'll put X in there. I kind of don't like that because it just turns into too many alphabets. The other problem is, or why I like to use these arrows is, I'm also right there in the equation declaring which way is my positive side. So I'm declaring moving towards the right hand side is positive, right? My frame of reference is if I go towards the right hand side, it's positive. So if a vector, horizontal vector, or any vector is pointing towards the right hand side, it's going to have a strong horizontal positive component. If it's pointing towards the left hand side, it'll be in the same direction, but the value will be negative, right? So instead of just putting X here, I like these arrows because it tells me where and what direction you're choosing, right? So not only is it horizontal, right is positive, right? Same with the vertical part. Top going up or going towards this direction upwards is positive, downwards will be negative. The other simple component, again, it's simple. So again, we're trying to see this as an O-level question, is that any force resolved will be, can be resolved in its components, horizontal and vertical. Now with the angle, so it might get difficult for people to resolve a force. So with the angle, wherever this angle is, it's always going to be cos. So if this angle was over here, instead of over here, let's say it's at 30 over here, it would be F cos 30, and this side would be F cos 30. It doesn't matter where the force is. If you're resolving it towards where the angle is given, is going to be cos of that magnitude, right? So over here you see the horizontal component, which is this. So this vector, the white one over here, this is going to be F cos theta, and the other one, the other side without the angle, well, we're only left with sine, is going to be F sine theta. So easy way to recall. This is how I remember how to resolve angles, and if it gets too complicated, I just try to try to compare it with a triangle of a similar geometry, right? Otherwise, any vector you see, cos with the angle and sine without the angle. Cos with the angle, sine without the angle. Moving on. And the third and most final point is, if an object has a resultant force, if it's moving, then that is equal to the sum of all the forces acting on it. I didn't have room, so I wrote it like this. I actually hate it writing like this, but like sum of all forces that are there is equal to the net resultant force. So with these three concepts, let's apply it in our question, and let's start with this point. All right. So we have seen multiple forces. We're seeing multiple forces over here. One force is not drawn. And, just to keep it simple, instead of, because I know the force is going to be somewhere like that, I can just tell, right? I'm sure you can as well, because someone needs to pull it this way to counteract that effect a bit, and make it move towards the right hand side. So this direction will be the resultant force. It's not moving that way, this way, or any other way, right? So I'll try to put and just to explain my point, I'll try to put the third vector over here in this direction. It's like that. And that is F3. Why am I doing it like this? I think it'll just help me with having less negatives in the whole system, right? So with this way, it'll just help me a lot. Let's go with that. So over here, let's write the equation down. So the first is, it has a net force acting on it, which is equal to F1 plus F2 plus F3. 3 is the force I need to figure out, but all of these forces combined gives it a net force. What is that net force? We don't know, but we know the mass of this object, and we know the acceleration of this object. So this object is essentially, this is essentially 30 newtons, right? Like, sorry, not 30 newtons, what am I saying? 2 times 3, 6 newtons. 3 times 2. So m times a, that's the net acceleration, that's the total mass. So F net is m times this, but at this angle, right? But I can go forward, I can say, let's figure out all the horizontal components for this. The horizontal component for each, I'll just call it H. The horizontal component is going to be, now I'm saying this value is going to be 6, right? Because m times 3, right? So the force net resultant, which is the vector not drawn over here, but we can kind of imagine it over here, where a is this little tiny blue vector, that's 6 at an angle of 60. What is the horizontal component of that vector? this component of the vector. So it's this force net with the angle 50. So that's going to be 6 cos 50. Let's put on that in there. 6 cos 50. 6 cosine of 50 degrees, right? Let's now try to resolve f1. f1 is where? It's over here, right? Now it's going to be f. So I can't resolve it over here. I can resolve it like this. It's going to be f cosine 30, right? It's with the angle f cosine 30, so it's over here. But it's pointing the other way. I've already set my frame of reference. Actually, I haven't, so let's do that. It's kind of unclear. Actually, the question has, I guess, right? This way to be positive and that way to be positive for vertical forces, right? So it's actually negative on that side. So I'll just put a negative sign to imply, and I'll make that vector point this way. So F1 is going to be F cos 40, but we know the force of F1 of magnitude 10. So it's 10. F1 has a magnitude of 10 cos 30, right? But this 10 cos 30 is actually pointing like that towards the left. So to accommodate that, I'll put a negative sign. Straightforward, because my frame of reference towards the right is positive. If vector is pointing towards the right, it's going to be positive. This one's pointing at the opposite. Similar story with F2. F2 is going to be, we don't know this angle, so this angle is 90. It's completely vertical. So sine 90 is 1. Cos is going to be cos, because cos is with the angle. If this angle over here is 90, because it is, cos 90 is going to be 0. So there is no F2 vector that has a horizontal component. That makes sense. It's completely vertical. All of its effort is being pushed into the vertical thing, right? So there's no F2, so I'll just ignore it. And then there's F3. F3 is going to be simple as F3. We don't know what's the angle of F3. I drew it exactly on the 50-degree thing, but I don't know the angle actually. It could be this way, it could be the other way. I just made a generic one. So let's call that angle theta. I don't know what it is. It's theta. But theta, the horizontal, let's actually write that down. I'm struggling for space. The angle of F3 is going to be theta. So the horizontal component is going to be F3 cosine of theta. Cosine of theta. Those are all my horizontal forces resolved, right? Pretty cool. Now let's try to resolve all the vertical forces. And we'll do the same thing. Why don't you pause the video for a second and resolve it? I think it's going to be very simple, and just compare the answers, or just play the video and we'll take a look. All right. But I'll go ahead and try to do it. And I shall, the vertical component of all these forces. All right, back to Fnet. What is the vertical component of Fnet, which is not drawn over here properly? We know this is the angle, angle is 50. So all of these more or less are going to turn into sine. When there might be a sign change here or there. Let's figure that out. Okay. So Fnet was 6. It's 6. And we're trying to resolve the vertical now. It's going to be sine of 50, because it's not this angle. I don't want to resolve it like this. It's the opposite of this angle. And if you want to do the harder way, you'll also realize the Fnet sine 50 will give you this way. But I kind of remember all the time that with the angle, it's cosine, against the angle, it's sine. So that said, it's going to be 6 sine of 50. And because I know it's going to point up, it's positive, I'm leaving it positive. What about F1? F1, I think, is going to be negative, because if I do F sine of 30, I'll actually get this vector, right? And that's going to be negative because my up is positive. So same thing as the issue with the horizontal one. I'll just put a negative sign. It's going to be negative 10 sine of, what is it, 30 degrees. And one good way to figure out if you're doing the right thing or not is it's going to be, the only thing changing is the cos of sine, very likely. That's a definite change. And the only other change that should happen is the negative sign or the positive sign. So if this part is not matching that part, and you're doing it in a line, if this part is not matching that part, okay, cos and sine is not matching. Actually, that's meant to happen. 30 and 30 are matching, 10 and 10 are matching. Now the sine might not really match, right? There could be a chance of sine not matching, maybe we'll see it. But if it's not matching, then we did something wrong, and that's a good way of checking out. So it gives you a lot of control if you do it this way, right? 6, 6, 50, 50, cos is now sine. Makes sense. 10, 10, 30, 30, cos is now sine, but there's all, oh, well, the negative sign not carries forward, but it's also negative. Coincidence, right? Now F2 is not here, but we remembered F2 being F2 cos 90, so we didn't bother writing it down. So this is going to be F2 sine 90, which is just 1, right? So let's confirm. F2 is just over here like that, and its vertical component is going to be, if this is 90, this angle is 90, its vertical component is going to be sine 90, right? Because on the other side, if this is cos 90, that's going to be sine 90, but sine 90 is just 1, so it's just F2, right? So that's interesting. So we put a 0 over there, but we're putting the entire thing over there. But in other words, we actually put F2 cos 90 over there. Now we're putting F2 sine 90, right? And it's going to be positive. And I won't write down F2 sine 90 because I know it's just F2, because sine 90 is 1. F times sine 90, or F times sine F, and that's the same as F times 1. So it's just F. Why am I saying F1? I meant F2, right? So this is just F2. All that talk for this. Was it worth the effort? All right, what about F3? Or unknown force, I'm gonna say, this is why I kept it over there, so all my F3s come out to be positive. I wrote sine down. Actually, I was just trying to test you guys. I wrote cos down. I meant to write sine down. 2, F3, sine of theta. Pretty cool. We have our two equations. Now you see, if we can put all of these values in the calculator, we'll have F3 cos theta equal to something. Then we'll have F2 is actually a value. So let's take that away and put in the value, which is F2 is, I think, 20. Yeah, it's 20. So let's just put in that in there and quickly resolve it, solve it, right? Simplified. So I'll have F3 cos theta equal to something, and F3 sine theta equal to something. Let's figure that out. All right. So once simplified, my two equations are coming to be, so the horizontal one, F3 cos of theta is equal to 12.517 newtons. And the horizontal one, F3 sine of theta, is coming out to negative 10.404. I'm putting in extra decimals in there because I want my answer to be accurate, and at the end of it I'll round it off to the right number of significant figures. Right now I have a habit of throwing numbers down, right? Makes me a little more confident in my answers and avoids any premature approximation that leads to a wrong answer, right? So the simplest way is making F3 the subject for both. This is going to be F3. There are actually two ways of solving from here, we have two equations, simultaneously solving them or whatever, we can get an answer. There are actually two ways of solving this, and I'll tell you both ways. Yeah, so 12, let's do the normal way, is going to be cos theta, and F3 is going to be equal to negative 10.404 over sine theta. F3 is equal to F3, so 12.51 cos theta is equal to negative 10.404 over sine theta, right? And I'll take sine over there and this number over here, right? Put that over there, put this over here. So I'll have sine theta over cos theta, which is just tan theta. I'll have tan theta is equal to negative 10.404 divided by 12.517. Now theta will come out to be, theta comes out to be negative 39.733. So 73. Let's go with 73 degrees. Why is it negative? So we assumed in our initial reference that kind of like this. Over here was the object. Over here was our tin can. We assumed was F3 was like this. And theta was like this. So this was our frame of reference for theta. So if it was 39.73, it would mean, okay, that's 10, 20, 39, 39.73. It's over here, somewhere like that, right? So we drew it accurately. So we didn't draw it accurately. It's actually not here. It's actually here somewhere. So the value is coming out to be negative. So it's going away from x, and it's negative 39.3. So the angle is actually like that. The actual vector is that, that's its angle, and this is 39.73 degrees. The negative just says from this you have to measure backwards, not this way around, right? And we knew that. We knew, so this is validating our answer, right? And right now we can put this angle back into F3, into one of the equations we had earlier for F3, and find out the magnitude of it. So I want to use, just for shizzles, I could use either or. I'll use the horizontal one. F3 cosine. Now it's, I know, going to be negative 39.73. Right. Now I am not caring too much about the angle of this. I, much like anyone else, get confused with the positive and negative. But I know where my F3 is, right? It's going to be downwards. It's going to be here. Whatever value I get is just going to be like that. So I'm just putting in 39.73, not worrying about the negative as a positive. And actually, if you put a negative value in there and a positive value, because cos is symmetrical about the y-axis, the cos function, so you'll just get the same response anyway. Anyway, so I'm just putting in that value. This is equal to, what was it? 12.517. So F3 is equal to 16.27 newtons. So the force, this force, not this one, it's not over here, it's actually here because we know the angle, and the magnitude of this force is actually 16.27 newtons. So the question was asking for the magnitude of F3. I'll just write down magnitude F3 is equal to 16.27 at an angle of, in the exam you'll have blanks and, angle of negative 39.9, 39.73. Maybe if you don't want to say negative, or maybe somewhere you'll say 39.73 clockwise or something like that, just to refer that it's actually away from the horizontal. It's like down, you're measuring downwards from it, right? If you see this answer somewhere else. So, all right, holding true to our promise, we're going to separate way. So we just found out a few minutes ago that, the correct answer, but before that, we found out the horizontal component for the vector F3 came out to be 12.517. The vertical component came out to be negative 10.404 newtons. These two are the components for vector F3. So I don't know where the F3 vector is. I drew it like that just to get an idea. But let's draw the components and reverse engineer. And so the horizontal component is a lot like this. The vertical component should be here, but it shouldn't really be because it's actually negative, but same direction, same orientation, different direction. It's actually going to be downwards like this. So let's try adding these two vectors up. Do that. And let's add them up. So this will be my resultant vector. And we can see this length is going to be 12.517, and the vertical length for this vector, or we already know it is 10.404. 10.4, let's go with that. Won't write the entire thing. So if you see this as a triangle, or even this part as a triangle, you realize the magnitude is just the hypotenuse for this triangle. So you can just say F3, or the magnitude of F3 is the square root of the square of the two components of it, right? We already know this, but yeah, taking a very visual approach to this. So it's 12.515 squared plus 10.404 squared. And my value comes out to be F3, which is 16.27 newtons, right? Moving on. So again, not really moving on, but this value is coming out to be 16.27. Actually, I wanted to just do this question over here. So let's erase this and find out the angle now. Now, angle I can figure out with anything. So if I see my triangle like this, the angle, well, actually I'd use this triangle. Otherwise, if I use this triangle, it'll be another step because I have to find this angle actually. So I'll use this triangle, but what values will I use? I can use, sine, cos, or tan, because I have all three sides for this angle. There's theta. Let's put that in there as theta, right? I want to figure that out. Now, you know what? I'll not use this value. This is the latest calculation I got, so it has one more step possibly for an error, right? So I'll actually, here's just a tip, because what if you got this value wrong? Then you'll get theta wrong as well. So it's just like common sense, so to speak. I know I did it right? I'm confident, but let's actually use values we're actually more confident, because the more calculations you do, the less confident, because there's always a chance of a silly mistake, right? So let's use these two values, right? So we'll say that's opposite and base. So I think it's a tan thing. Opposite and base, no hypotenuse involved. So of course tan. So tan theta should be equal to, let's get a nicer color out. So much for nicer colors. It's going to be tan inverse of the opposite. 10 point, it's 404, even though I've written down 4. And divided by 12.517. And theta comes out to 39.73. Wow, look at that. So why am I showing this to you again? It's pretty straightforward. 2 reasons. One is you try to solve the question as you feel comfortable. Some questions, some of the better questions to practice on are actually, counterintuitively, are just one question, and it's a big question, so they haven't highlighted the steps, so you're in complete control. So that's scary, but that also helps you decide your own way. Whatever you're good at, you'll use those methods and figure out the answer. I actually like this particular method more rather than the simultaneous equation, because it just makes more sense. And I feel I could have done it faster, right? Okay, let's do a quick recap of the question. The question started with just a tin box, and there were 3 forces acting on it and a resultant force. We had to find one of the missing forces, which was F3. We assumed F3 in this direction because our F3 resolution vectors, even though we knew F3 would be here, but resolved F3 would be positive. Otherwise, if this was here, I'd have to put negatives and whatever, so it would have gotten complicated. And I was ready that my vector was here. Sometimes you might not know, so sticking to your, so this will help you really figure out, questions like this will help you figure out what part will come negative. If it comes negative, what does it really mean? If the angle comes in negative, depending on your situation. What if another person is doing the same question and their initial theta didn't come out to be negative? They probably used a different frame of reference, right? Anyway, so we figured out that this question, well, we understood the question. The second part we figured out is that it's a simple question. The only problem here, the only challenge here is there are a lot of forces. And here's some skill building for us. How do we manage this question where there are just so many forces? Well, we understand first that it's just resolution. We've done it a million times, so we can do it 3 or 4 times in one question, right? So we did that. We set up our equation. These are how the forces are balanced. So the horizontal component would be cos of each of these, because that's how the angles are laid out, right? And the vertical components would be sine of each of these. Yeah, there's no sine over here again because it was sine 0, so it came out to be, sorry, sine 90, so it came out to be the full value. So I didn't bother writing it down because it just got messy. And this way is really good because you can compare the values and say like, oh, 6 and 6, 15, 50. I'm still talking about the same vector, so I didn't make a typo while writing it down, but cos is changing to sine. That makes sense because I'm not talking about the horizontal vector anymore, I'm talking about the vertical vector. This is a very powerful computerized way of looking at your equation, and another step in foolproofing your method, right? Because it's so easy to get lost in the way when you're dealing with so many equations. So this helps us mitigate that. And once done, we found out f3 cos theta equals to this, f3 sine theta equal to this, and we have 2 unknowns, 2 equations. That's a simultaneous equation, classic case, and we try to solve that like so. Classic simultaneous case, I won't talk too much about it. It's straightforward. And moving further to the more interesting part was that putting the vectors back together again. So that was just reverse engineering. We first divided it into components, solved the equations, now putting them back again. So this was also straightforward. We found the angle and the resultant force, and it held true. Our vector was indeed in this area, in this direction. We had a very good idea as to where it would be, right? Furthering on, we got our answer, but we also talked about another approach of taking components and finding out the vector from those components, which was just assume that it's a triangle, because that's how most vectors work, and finding out the hypotenuse would give us the magnitude. Then we could have used tan to figure out the angle, right? And we use tan instead of cos or sine because I didn't want to use the hypotenuse, because that's just good practice. This is the latest in the step of values we got. So if anything, between this value and this value, like if this value is wrong, so is this value, and your entire question is wrong. But if this value is right, there's a chance this could be wrong. So, you know, Pascal's wager. What is the easier, what is the safer bet? So I use this. And again, you don't have to think too much about it. Over time, it's good if you do it. It'll maybe help you. But it's just, you know, once you start doing a lot more questions, you want to use everything to your advantage. And I think just thinking like this just makes you a little more confident, rather than, oh no, I got to think about this as well. This is just a slight tip when you're doing too many problems. It's something I do. I'm a person who doesn't like doing too many long equations, but I've gotten good at it because I like to, you know, see my advantage in this way. And it just changes the entire question for you, and it turns it into a very, it makes it a lot more intuitional. I'm like, to anyone seeing this right now, probably this seems like a lot more common sense. Maybe it wasn't never highlighted to them. It was never highlighted to them by a teacher formally, but this is just common sense. You would half the time do it, but why not put it into practice, right? This will really help you guys. All right, I hope you guys enjoyed this question. It was really long, but we went and really tried to do this question as an O-level student who just figured out what vector components are. Everything else, more or less, maybe slightly advanced math, but everything actually is something very easily doable by an O-level student. And if you find it difficult, it's okay. Don't feel like, oh, if an O-level student can do this, I am having difficulty, so maybe I'm not good enough. That's not what I'm trying to say. I'm just trying to say you can take this big, huge problem, divide it into tiny little steps, and tackle one step at a time. That's why most problems are just not problems, they're just tedious. There's a difference. Anyway, I hope this helped, and I'll see you in the next video.